I'm going to keep my eye on chat throughout here. And we'll go ahead and kick things off. So welcome everyone to our March ECSS Symposium. This one is a unique treat for me, rather than featuring ECSSers talking about their ECSS projects, which is what we've done for probably the last 6 or so years that we've been doing these symposium. This is the first time that we've got PIs actually presenting on the call and talking about their work. We've had a fair number of PIs attend the calls, but not in this kind of format where really the focus is on the PIs and their experience. So I really want to thank our PIs today for taking time out of their busy schedule to agree to be on this panel with me and discuss their ECSS experiences. Hopefully we'll be able to field plenty of chat questions from the audience. So if you've got questions that come up while people are speaking, type them on in and I'll try to field them during the call. So with that, let me introduce our first PI, that's Michael Cianfrocco. He is a research assistant professor at the University of Michigan's Life Sciences Institute. And Mike's ECSS project involves analysis of cryo-EM data on the COMET and previously Gordon systems at SDSC. And so with that, I'll let Mike tell you a little bit more about his work and his involvement with ECSS.
Okay, great. Thank you, Nancy. So it's nice to be here. I'm glad that I've had the opportunity to receive ECSS support and also get a chance to tell you about what we've been able to do with it. So for us, the project area is this field of protein structure research called cryo-electron microscopy. This is a technology that lets you solve protein structures using electron microscopes. And so for those who are actually interested in this, if you go and look at the Nobel Prize in Chemistry for 2017, you'll see that it was awarded to 3 scientists in the field who really helped pioneer this work. And so this is a technology that's come a long way in the last 40 years, but really in the last 5 to 6, it's really taken off. And that's because we've had improvements in detectors and microscopes and algorithms. And what this has meant is that we're able to now solve protein structures that we couldn't solve before. And for those who don't do proteins in biology, we care about the shape of proteins because the shape of a protein tells you how it works. And so the same way that if you're trying to study how cars move on the highway, if you had no idea what the difference was between a truck and a bus and a car, if you had no idea if their shapes were different, you wouldn't understand why a bus could carry 4 people, but a truck could carry 2. And so for us, that matters a lot for proteins. And this ends up being a big deal when it comes to disease research, cancer, neurodegeneration, viral infections. This all relates to proteins and the shape of proteins. And so we care a lot about this. And so this is a really powerful technology that's been taking off. But the problem that we've come into really fast is that the technology gives users terabytes of data, and the vast majority of users that want to use this now are no longer experts in the field of cryo-EM, meaning that they have less Linux experience, whereas previously you had to come into our field, you had to learn sort of command line, supercomputer type resource management, and now users don't have that. And so this is where I entered this. So my experience with ECSS and XSEDE was being at UCSD as a postdoc. I eventually was able to meet up with Nancy and also others that directed me towards ECSS and also the fact that these resources exist. So I think for me, if I had known this existed ahead of time, this would have been really important to know, because I think a lot of people don't realize the sort of fantastic support you can get through this. So hopefully there are people here who can learn more from this from me. But so I was able to meet up with them, and the sort of crafted the idea for ECSS support was to take a previous existing platform of a science gateway called Cypress and sort of port it over to cryo-EM. And so the idea being that Cypress is very popular, very established, mature website that users could use to submit jobs to COMET or Gordon. And so we were able to sort of copy that over, and then we had to integrate some other things. And those things included Globus file transfer service so that we could actually upload terabytes of data through a web portal, and mostly just handling that. And so that's been where I think most of the ECSS support has come in, is sort of first off making this happen. So I think for me, the question that I was asked at some point by ECSS, probably by Nancy, was sort of what would have happened if we didn't get the support? And the answer was we wouldn't have gotten anything done because the level of sort of expertise required to sort of build a website on top of Comet or Gordon at SDSC is very specific. And even though there might be people who are computer savvy in the field of cryo-EM, it still would take us a long time to do this. And so I think the ECSS support really helped us think about a problem differently, which is how can we do this sort of science gateway or this web-based approach to data analysis. So it's still taking us a while to do this because it's still tricky. The details matter a lot as far as how you build this gateway, but through help from ECSS and also the Science Gateways Community Institute, we're really close. We're extremely close to opening it up. And so that's exciting for us. So I think that's it for the little overview, unless there's follow-up questions from Nancy.
Super, thanks, Michael.
Okay.
I think we'll probably run through and have everyone speak briefly. Also want to encourage everyone on the line to type in your chat questions throughout, especially when we get to the discussion period. And it's going to be really interesting because you're going to hear from 4 really unique application areas. And I think that's going to be one of the things that's so interesting about this call. Cameron, you are up next. I think you're going to share some brief slides. So why don't you go ahead and share your screen. So Cameron is a computational scientist at the Scientific Computation Research Center at RPI. And Cameron's work is on adaptive finite element simulations for complex industrial flow problems. So, you know, really unique application compared to what Michael just described. So Cameron, if you want to describe your work a little bit, that would be terrific.
Sure. Thank you, Nancy. And I appreciate everyone attending here. Hopefully we can share some positive experiences and help you transition into your own interactions with ECSS. So the background on the Scientific Computation Research Center where I work as a research scientist, we specialize in developing technologies for engineering type simulations. We're in Troy, New York. There's a little nice picture here of what it doesn't look like now. It's very snowy and more gray, but that's coming. So we run on the largest systems that we can get access to. So all the big NSF and DOE systems, do unstructured meshes based on CAD models, and we'll show some pictures in the next slide. So, you know, we have a bunch of software that's accessible. You know, a high-level overview is at this first link, the squark.rpi. And then we have a GitHub with multiple repos where you can find different pieces that I'm about to discuss here. So just to give you the reference for what these engineering type simulations are, we have a CAD model of this suspension upright for the RPI Formula hybrid car from 2014, as it happens to be. And we apply a load to it and we study how it reacts under load. So to do this in big parallel systems, we need simulation management and modeling tools that talk to the CAD kernels, Parasolid, ASYS, ProE, etc. We have to understand fields on those models and establish the relationship between the fields in the model via attribute control systems. The different parts of our analysis have to talk to each other on different processes. So we do neighborhood aware message passing. There's this PCU component, which is in the core repo. We have load balancing, and we have reordering to improve cache performance and such. So if you haven't guessed by now, my main research area is in software and computer science type things, not domain-specific knowledge in mechanics or mathematics. So some more fancy pictures. We have a linear accelerator with a particle traveling through it, and we're sort of tracking the particle as it goes through and adapting the mesh. Then below that is a adaptive blood flow simulation using the PASTA CFD code. And then actually another PASTA CFD on a vertical tail structure with active flow control elements on the trailing edge. So we're trying to form the sort of lift and drag characteristics of the wing by controlling these piezoelectric actuators on the edge, and you can see there's a large array of them. So this requires adaptive meshing and very large scale parallel computation to drive these large systems that we have access to. There's many other applications that do similar types of things with adaptive meshing. We have a couple of fusion projects with XGC1 and M3DC1, where you start putting particles into this unstructured mesh and have to track them as they move between mesh elements and different processes. We have an interaction with ERDC Proteus code, which we have a two-phase problem we're working with them on, with adaptation. And then Albany Multiphysics from Sandia National Labs. We've looked at ice flow simulations and semiconductor thermal creep, which is a type of manufacturing consideration when you're forming these large arrays of solder balls and such. And then we have a parallel hierarchic multiscale project for modeling soft tissues. So just some more of a deep dive on what a mesh is and CAD and such. In the bottom right, you see the upright again, the CAD model as you might design it in whatever Pro-E or SolidWorks or NX. Then you create a mesh on it. We don't generate meshes in particular. We use the Symmetrics mesh generator. It's a spin-off from our research group in the mid-90s. But we can interact with anything that produces a valid mesh. But creating a valid mesh of complex geometries is tricky. And then we distribute it, we create a partition. This is a sort of exaggerated cartoon figure where I've kind of exploded the parts into separate chunks, we actually put an air gap between them so you can see how the different parts that get assigned to processes connect to each other topologically. And that's one of my special research or focuses and researches in the load balancing and creation of these sort of compact parts that we give to different processes. And we use standard graph partitioning and load balancing tools for that. So we're funded for doing this stuff on the really, really big machines. So the exascale computers that are coming through FastMath and the ECSSEDE extreme scale discretizations project. And this is my cheat sheet for answering some of the questions we were going to be asked. So how did we get involved with ECSS? We did an XSEDE extract project. We were looking to reduce the time to improve performance on the KNC and then KNL systems. We were successful. We learned a whole bunch of stuff. We established some great connections with TAC, ECSS staff, and the Gateway team. I saw Doug James was on the call. Hello, Doug. For people looking into ECSS, I think there's a number of hints and lessons learned. I think one of the key things was establishing the goals and fine-grained milestones, problems, and documenting how to get to those points where you can test and do the actual developments is really important to speed things up. So it's my fairly brief intro.
Great, Cameron. Thanks very much. Yeah, you kind of segued into a few questions I'll introduce later, especially about suggestions for improving ECSS and how the experience might be better. Those are things we'd love to hear about as well.
Sure, and I can certainly elaborate on those.
Okay, super. Is the audio okay for everyone on the call? We had someone say they were experiencing some interrupts. I haven't heard that on my end.
Sounds okay to me.
Okay, super. We'll let that go and move on to our next speaker. So Jian Tao is a research scientist in the Strategic Initiatives Group at Texas A&M, Engineering Experiments Station, and the High Performance Computing Research Group at Texas A&M. So Jian, please tell us a little bit about your work with the coastal model deployment on XSEDE resources.
Thank you. Excuse me. So my name is Jian Tao. I'm a research scientist at Texas A&M Engineering Experiment Station. I'm also affiliated with HPC Center here, High Performance Research Computing Center here. So my primary role here is basically to help the researchers to use HPC systems, and building and maintaining science gateway will be one of my primary interest to serve people at A&M and people from the much wider coastal modeling community. So the project we started was back when I was a research scientist at Louisiana State University. And Louisiana, you know, it's a place where a lot of hurricanes and storms surge every year, and people have been investing a lot of money in that. And so this project started as a collaboration among 3 states, universities in 3 states like Alabama, Mississippi, and Louisiana got together, got EPSCO funding. And we started as one of those, probably I'm not sure how, it's a lot of money, $3-4 million project. So simulation was one of the proposed gateway for users to use computing systems to simulate the storm surge, hurricane, all this kind of stuff. And we got started from that project, and then we moved on to another project after that one finished. It's called the CyberSeas project. So that project is different from the previous one because in the CyberSeas project, we are proposing to do something relevant to cloud computing. So that's something when, let's see, first Max and also Mona Wang from SDSC started helping me to try things out on Comet. So our users basically, they want to run some stuff, and they don't want to mess around with the command line tools, just like many other users the previous PIs mentioned about. There are more, because all the engineers that I have been in contact with are not all of them, but most of them are more familiar with Windows, you know, this kind of interface, and Mac kind of interface. They are not you know, familiar with Linux at all. Also, for a lot of users we are dealing with, they are from industry. You know, they are doing all the modeling work, consulting work for others, and so this kind of portal will help them to, you know, communicate, help the academia and industry to exchange ideas without worrying about IP issues, because all the stuff we shared, we pack it up, and we can easily put it in the container image and share them among the different parties. So for the ECSS support, Mana Wang is my primary contact. Actually, I started with working with Matt, and he helped a lot to getting all the documents ready and helped me to get started on Comet. He also helped me to compile things and do other stuff, you know, that I cannot do it quickly when I get started there. And also Mona helped a lot with all the posters, all the manuscript stuff. We are just working together on a couple, at least probably 2 posters. And we also worked with people from Globus team, Stu Martin, and I think there was another one, I forgot his name here, it's Eric, I believe, I forgot the last name. So they were both working on Globus. So we talked with them about how we can make use of their authentication module in our container-based framework to see how we can authorize users to leverage all the Globus transfer or other stuff. And it worked. You know, we tried a couple third-party tools, and it didn't work out finally. One of the main reasons that the people I talk with here, they lost interest about using that. They prefer to get things handled in a more traditional way. But we are still keeping all the modules we developed there, and so we can leverage that in the future project. But it's just, you know, some redirection of the research priority there. But again, for the last 2 years, we have been working closely with ECSS personnel and to get all the stuff set up and running. We do have one of the really working functional websites setting up at Quarry, which retired not so long ago. And we have been using that machine for a lot of demonstrations. And you know, as a research portal, we did have some plans to make this long-term, but again, there were some other maintenance, other issues. So we just keep the image there, temporarily archived, and hopefully we'll bring it up in the near future after Corey retire. So, well, I think that's roughly about it. Mostly about the technical side. On the coastal modeling side, it's a standard. I don't think, you know, people will be more interested in that. They can go to our website, simulation.org. They can look more into the science part, mostly on inundation, flooding, and hurricane simulations. Yeah.
Thanks, Jian. So SimiLotion launches flooding applications on XSEDE resources. Sorry, that's a question. Yeah.
Yes, yes.
Yeah, okay, yeah. Okay, great. So we've had cryo-EM, we've had finite element and mechanical engineering, we've had storm surge modeling, and now I'd like to introduce Sever Tipei. Sever, is that the correct pronunciation of your last name?
Almost. Sever Tipei.
Sever Tipei, okay. Sever is a professor of composition theory in the School of Music at University of Illinois College of Fine and Applied Arts. So his project involves music composition, and I'm really interested to hear about this as a nice juxtaposition to the previous talk. So thank you very much for making time to speak with us today, Sever.
Well, thank you for inviting me here, and thank you for XSEDE and all their help that they gave me. Probably you would wonder, what am I doing here? I'm a composer, a musician. My training is as a musician, and only an amateur programmer. But I was practically all my professional life interested in computer music. Now, you might know that computer music started at the University of Illinois in the mid-1950s with Lejar and Hiller, who was actually a chemist. And he was hired at the university to teach chemistry. But he pursued also a master's in musical composition and was the first human to use a computer to compute a score for a string quartet. The Iliac Suite, which was performed in 1956 and then in 1957. Let me take you a little bit through history here and say that although people don't usually realize this, but there always has been a link between music and mathematics or science. Not very profound, but there, from Renaissance and going to composers like Debussy and Bartók, people have used the Fibonacci series of numbers in their compositions, and we know this for sure. Now, about the same time as Hiller started computer music at Illinois, a Greek composer living in France, Yannis Xenakis, started writing music using stochastic distributions, and then he went on to Markov chains and set theory and group theory and game theory and random walks and so on. So I was always interested in such things, and but I was born in Romania, and I went to college there, and there was no computer available at that time. But once I arrived in the United States, I learned a little bit of Fortran and started programming my own applications. So at the beginning, I was interested only in computer-assisted composition. In other words, using the computer to generate a score for live instruments or voices. Using different logic for that, and I'm not going to go into details. I was I was using the NCSA resources, the National Center for Supercomputing Applications, almost from the time that it was created here. And at that time, of course, everybody was asking, why do you need a supercomputer to do this? And it's a good question. It was more like, you know, trying to be associated with this. However, a little later, I also started being interested in digital sound synthesis. And there, you might argue that one could use a supercomputer or a larger computer. Why? Because sounds are produced in the standard system that we have today at least 44,100 samples for a second of sound or silence. if each of these samples are the result of relatively complicated computations, you can see how things are mushrooming and getting bigger and bigger, the project. So right now I can say that I do need a supercomputer to do sophisticated things. You can do very simple things and you can use your iPhone for that. But if you want to do something that it's fairly complex and sophisticated, you need something more, more developed than that. I do have a student right now, and his composition, it's like a sort of a, it's been tested at XSEDE at San Diego Supercomputing Center, and he uses a method called granular synthesis, where each sound is actually a small grain of a few milliseconds. And his composition of 8 minutes contains over 770,000 such grains. So in order to compute that, even now at San Diego, it takes almost about an hour on the supercomputer. Or our goal is to do such things in what we call real time. In other words, the computation time should not exceed the time you need to listen to the piece. So this is the project right now, and this is the goal. At San Diego, Paul Rodriguez and before Robert Sinkovich have helped me to parallelize the process. Right now it's just multi-thread, but they are working and they are getting pretty good results, but again, we are not yet there at real time. But that is the goal. Now, the software that we are using, that I'm using, has been created at U of I, the computer music project that I am directing, and at Argonne, starting in the 90s. At Argonne National Laboratory, where I collaborated with Hans Kapper, a mathematician, now retired. And we worked on the synthesis part, which is, I dare to say, fairly complicated and very, maybe better than many others. but also, since Argonne is not dedicated really to music, we did this under the cover of sonification. And we did some, we had some results, interesting results in that area too. Now, I don't want to abuse my time, but let me say this, that part of the project, it's also this idea of mine, which is actually borrowed from an idea that was circulating among composers in the 60s and 70s, which is that of a class of compositions. I call them manifold composition. In other words, you have a plan, a structure, and a computer program, but the computer program involves redundancy at many levels, from the makeup of a sound to the big shape of the piece. Now, if you just change the seed for the random number generator, you'll get a different variant of the same piece. And that depends on how much randomness you introduced and where, okay? But then you can create a theoretically infinite series of pieces that are part of the same family. I like to use this metaphor. It's like faces in the crowd. They all have noses and eyes, but each of us, it's different. So that is my, my interest. The next step in the project will be to have a piece that is, as I like to call it, a brewing piece that keeps computing all the time. And now and then you go look and take a sample and perform it and see how it is. Now, of course, you can play games with this. Say you start with few options, let it grow, and then reduce the options and make it die. So it'd be like something, an entity that's alive. No, we are not there yet, but with the help of the San Diego people, we might one day arrive there. So
Sever, thank you so much. This is fascinating. I'm sure everyone on the call is wanting to hear one of these pieces as much as I am. So if I don't know if you can put a link in the chat. Otherwise, we'll make sure to get one up on the symposium website. But this is really fascinating. I think you also worked some with Alan Craig, who's in the novel and innovative projects area of XSEDE and can serve as a translator, I think, between some of the domain areas that are less, you sounded quite computer savvy yourself, but I think a lot of people would not be in kind of translating what's wanted into something that supercomputer interfaces and administrators and things understand.
Well, I'm doing in writing the code. Am I on?
Yeah, you froze for a minute for me, so I stopped my video. I figured it was networking at my end, but I can hear you now.
Yeah, yes, I met Alan a long time ago at some NCSA symposia, and we've been knowing and being friends since. And a couple of years ago, I also, quite by chance, met him, and he told me about XSEDE and all these programs, and he was instrumental and extremely helpful in getting my connections there and setting up this whole experiment. Now, I would like to add something else. You said you want to put the music online. My experience has been in the past that when I talk about this, everybody gets very interested. And when I play the music, the interest kind of deflates. So I hope that that's not going to be the case this time.
No, I think it's really fascinating. Some really fascinating ideas here too about the variations on a theme and letting the music grow in different directions. And yeah, I've not had much exposure to computer music. I know it's a strong field here at UCSD also, so I'm interested to learn more after hearing you speak. We had a chat question come in for the speakers, which is around whether there was something interesting or unexpected that happened as a result of going into, or as a result of getting the ECSS support. So basically, you know, starting off, what did you sort of envision happening? And then how did what actually happened change? Were there any surprises along the way? That sort of thing. So maybe I'll put this to Michael first, and then we'll move through our speakers and see what folks have to share about that.
Sure. I mean, I guess for me, I feel like I've been going kind of down a rabbit hole now with sort of different aspects of Science Gateway and now Globus integration into our gateway, where when we started this idea was, can we make a website that could connect users to supercomputing resources? And then now suddenly I'm presenting at the Globus World Tour in a couple weeks. And, you know, I'm sort of becoming into this world of higher level thinking about your data. Besides just running the data on the supercomputer, it's going to be data management, user interface, user design. So I feel like it's just been kind of this sort of an onion that I keep on peeling and learning more and more and getting deeper and deeper into this field.
Yeah, that's a great analogy. Thanks. Yeah, I think kind of leads you in all sorts of different directions that, especially as a domain scientist coming in, you don't really expect to go necessarily. And hopefully they're places you want to go.
Mm-hmm.
Cameron, I wonder if you could comment on that as well.
Certainly. So yeah, we started by scoping out a agenda that would chase after performance on KNC and KNL. And it led into a gateway with the Science Gateway team, and some great sort of collaborations with the staff at ECSS, TAC, and obviously with the Gateway folks that have been meaningful, because I see these folks at conferences, the XSEDE conferences, but elsewhere, and it just really sort of broadened the community a bit. So.
Yeah, so what led you to think from performance optimization on the Knight's Corner and the Knight's Landing to thinking about gateways? It seems a bit orthogonal, I guess, from the outside.
It's the problem that was already mentioned, is that if you have a software stack that does something useful, but the barrier to entry is very high, then how do you address that? And one answer is a web-based gateway that you sort of you distill out the tricky bits, dealing with the file system, dealing with network issues, dealing with the terminal, Linux, GNU Linux command line, and just make your stuff more approachable and try to expand your user base. The gateway obviously can't support your most sophisticated users running at the largest scale, but it can get students or beginners going at least, and at least get them to the small to medium scales.
Yeah, thanks. So kind of an interesting experience starting out in one direction, which was pure optimization, and then kind of ending up in maybe quite a different space with much expanded access to the software. Yeah, thanks, Cameron. Jian, we saw your video briefly. I wonder if you could speak about some kind of unexpected developments that happened with the coastal surge modeling simulation gateway.
Yes, so I just probably get back to one of the questions that you just mentioned, is that to get more out from this collaboration, it's not just, you cannot just say, this is a computer science problem and give it to an ECSS team and let them to handle it. You needed to get some expertise on your own team to, work together with them to solve problems. And by doing this, we can, during the process, we do have 2 or 3 students trained. They learn a lot from our collaborators from the ECSS team, and also they learn a lot from us. So the students are trained during the process. So we get someone in between to just work on both sides, so they can learn something and do some work for the project. And for the simulation project itself, so one thing I noticed that's very good about this ECSS support is that it's not like you're getting money from some big source, and then you are required to use some existing software they're developing. So ECSS itself is providing this help, just let you to use the resource, and not like give you any. There are no conditions attached to this. So I think this is important, because for some project, if you want to get help, get something, needed to either use their software or more or less connect to their existing software framework, and doing that therefore more or less limits your flexibility, your project. And as a science gateway developer myself, I'm kind of like to have a more flexible software stack that I can handle, giving me a very big chunk of software infrastructure that can support existing framework. Might be working for a temporary while, but the problem is for the maintenance issues. Whenever someone leave, or something happened to some of the developers, the whole project will slow down. So we start with very flexible components, and then we get pieces together, make sure each one understands some parts of it, and then we gradually can teach each other. Then we get things working together. So there are some cons and pros about using existing matured framework doing this science gateway development. But my personal opinion is probably try to do something, at least try something yourself to see if you can start from smaller or more microservice-based components, instead of directly jump into some existing big frameworks that can help you do everything at once. Whenever you need to do something extra, you will spend much more time. Yeah.
Yeah, a couple of really good points. Thank you. One was involving members of your own team, especially students, in the actual project, so that at the end of ECSS, you feel like you're more prepared than when you left, and you're ready to kind of march on with folks on your team who understand how to move forward. I think that's something that we really try hard to engender, and I'm glad that worked in this particular project. I also like the comment about not having to use a particular type of software or framework or technique. I think that's one of the things that we'd like in ECSS, is that we can be technology agnostic. As long as you're using XSEDE resources, we can work with you to make a use of them in the best way, using whatever software is most effective. also, I think we can kind of change supporters as the needs of a project changes through the course of, a year or multiple years. Oftentimes we'll see, a project starts out with optimization, and then maybe it leads to visualization or data analytics, and then possibly there's a gateway component later on. But being able to kind of interchange people throughout, hopefully is something that can help other PIs as well. So it's not sort of a constrained process. I guess also if sort of the project, a lot of times these don't often unfold exactly the way the work plan dictates, and probably some of you can speak to that as well, and just sort of, how you are able to sort of adapt to changes through the course of the project is something that we might talk about also. I guess probably, let me bring that first question back to Sever yet, and that was there something interesting or unexpected that happened as a result of the ECSS work? So you mentioned this goal of moving towards these pseudo real-time simulations. Were there things that happened while you worked up to this that kind of surprised you or weren't what you expected?
Well, yes and no. There were little things that I'm not sure they deserve being mentioned. The program, the software, it's in C++, but there are three main parts. So one is the composition module, that it's closely linked to the sound synthesis module. And on top of it, it's an GUI, a graphic user interface, which produces an XML file where the data is stored. In order to read that, you need some parsers. And I always met this problem with making the parser work with the rest of the program in different environments. But again, that's not really a main thing, and it was solved pretty fast. The surprise, in a way, was that you can use a lot of nodes and a lot of cores, but there is a limit, after which you need intelligent intervention from the people trying to operate to write the parallel system. And Paul and Bob were very good at that, and they are still working on this, because the machine won't let you go much further because of the communication between the nodes. On the other hand, I can talk a little bit about the fact that each time you produce a piece, it is something new and something that might amaze you. Somebody who used to teach here at Illinois, Herbert Bruin, used to say that he didn't learn how to like his new piece yet. In other words, you are surprised by the results. You know what you want to do, but the actual output might be different and surprising, and you'll have to learn to accept it unless you discover that there are faults in the logic or in the program.
I like that expression. I haven't learned how to like the outcome of an ECSS project yet, but eventually.
That's right. Well, you know, it's a little bit like, I dare to say, like fundamental science. You know, you don't really know always what the experiment or the theory will produce. And that's the interesting part.
Great. Yeah, thank you very much. I wonder if people could speak to kind of what you would advise someone else who's thinking about ECSS, what you would advise them on in their decision making. What would be kind of the most helpful preparations to going into a project? What kind of expectations could they set? just kind of giving someone a general sense of what this could be like for them. And maybe we'll circle back to Michael one more time on this, if you don't mind.
Sure. Yeah. I mean, I guess advice. I mean, I guess the bigger thing is knowing that this exists. I think, in my opinion, because I think once you realize that, oh, as a domain scientist, you can reach out and get sort of expert level support for things that range from code optimization to building science gateways. That's just amazing, I think, to offer that. And I think expectations are that it's still science. This is science, and science takes time. And so that it might take, it might seem quick for you, but it actually getting everyone together on the same page can really take some time. I mean, I guess I've been working now with Mona and sort of through ECSS and Science Gateways Community Institute for over a year, I guess, along a year and a half perhaps. And we're close, but it's taken a while to do everything we wanted. We also were trying to do something that no one done before. So that's also why.
Yeah, no, that's really good, that there is this kind of component of research and the unknown. Anything in terms of the kind of, regular meeting times or carving time out of your other activities or having people on your team who are actively involved. If there is a team, I think, Michael, I know for you, it's just you. It sounds like Jian had a team of students on his. Kind of suggestions around that for achieving the most, or?
Yeah, I mean, I do. I'm sure having a team would have been really nice. I mean, I think that's the hard part about when you're hitting on these kind of interdisciplinary areas where it seems, at least for me right now where I am, there hasn't been other people that have jumped up to join this with me. So it means I'm sort of spearheading it when I was in San Diego, and now I'm in Michigan, and it's still me. And so getting someone who's interested in sort of, cyber infrastructure building, website design, layout, but also interested in protein structure. And, it's like a very narrow niche. And so I think a team would be great. And I would definitely recommend at least going in with multiple people to sort of keep everyone honest and also on top of the task at hand.
Yeah, great. Well, it's nice to be working with you in your pioneering role. We'll all be able to say we knew you when. Cameron, I wonder what you would have to say to someone thinking about ECSS and kind of best practices for a fruitful collaboration.
Sure. So I touched on this a bit in my cheat sheet slide. The master apprentice sort of training approach really doesn't scale. So if you're trying to onboard somebody to use your tool, especially if you're trying to optimize some kernel or something, holding their hand as they learn how to run it and learn how to change the input slightly and all that stuff takes a whole lot of time. So developing documentation is going to benefit the ECSS collaboration for whatever those specific tasks are, as well as establishing some documentation the whole community or user base can reference. And I found that we had some documentation when we started, but it got strengthened in several areas just to make those communications quicker.
No, that's a super good point. That's something that we often see in projects, just by the fact that you're bringing in someone from outside the team and have to bring them up to speed. It kind of helps the team understand all sorts of other things that they probably should have been doing, like documentation, sometimes like version control or software engineering problems that practices that allow someone else to participate. That hadn't been in place necessarily previously because it was just a small group working on the code or something like that. So yeah, good point. Jen, I wonder if you could kind of share your experience as far as recommendations for someone going in and sort of what it takes to achieve success in one of these collaborations.
Sure. So I think the very first thing is to keep in mind that when you start working with people from ECSS team, is to make sure that you understand that you don't have anything to lose. So all you get is just what you will be getting from this, and you're not supposed to be losing anything from this. So don't be afraid to try things out, even if it's not working at the beginning, you might feel it might not fit this well. Just give it a try. You know, they are very nice people, and they are trying to see how they can help. So on the ECSS side, I think the only barrier here is just like 1 page or 2 pages of public proposal. I'm not sure it's an application, right? So after you, when you submit your XSEDE allocation proposal, you can just attach probably 1 or 2 pieces of paper to get some extra information that what you need for support and etc. And then just ask for it. And I think a lot of people, I mean, here at NIM, Texas A&M, I'm providing similar services to people who are going to use our local systems. And I think they are kind of worried about first, they're worried about there will be some monetary burden. But even though we're providing free services. And secondly, it's about the extra probably paperwork that they need to fill in, even though just 1 or 2 pieces of paper, you know, forms they need to fill in, they're still kind of like, you know, don't want to try that. So I think it's the very first thing for people to benefit from the support team from XSEDE is just try things out. Don't be blocked away by you know, your laziness, and just give them a try and try to talk with them to see what they can help. And I would suggest that if there will be a channel, you know, even before they start writing all these papers or other things, it will be better to set up a channel that people can talk or chat with the ECSS, you know, team members about their problems and about their, you know, the issues they want to resolve before they start doing the application, submit, those kind of stuff. One way, you know, they might not get rejected easily if they submit something that doesn't match this requirement at all. They say they might get rejected. They feel, you know, disappointed. But if you just talk with them, find a channel to talk with you guys, then it will be easy for them to, you know, get along with all the support and all the resources available. So for those who want to jump into this and to start using all the XSEDE resources and the support from ECSS, I would say just, you know, just start doing that. You know, if you wait, someone else will jump in this and you will lose the resource might be available to you. So I think that I have nothing more to say about this. That's
and thanks. You raised some really excellent points. I'm not taking notes, but I'm going to listen to this recording afterwards and take those notes to make sure that we change you know, some of the documentation that we have. You brought up a couple of really excellent points. One I thought was that you get more by putting in more. So really kind of jumping in and setting your expectations high and trying to get as much out of the collaboration as you can. Another one was the paperwork. We call these the 5 questions in ECSS. So when you request ECSS, there's 5 questions that you get asked. And it's largely about what you hope to achieve with the collaboration. And that helps us make the right ECSS experts with the right research projects and, you know, come up with something successful that way. We talked actually at the last XSEDE quarterly meeting, which was just a few weeks ago, about the very feature that you mentioned, which is the sort of chat ability to ask questions before you go through and put in a formal request. We didn't think we'd be able to do something that would be very functional because the type of questions that come into the XSEDE help desk are just all across the map, and they're usually involve farming out email to the right experts, whether it's at a service provider or ECSS or allocations or wherever. So the help desk folks didn't think a live chat would really work, but what we're gonna do is kind of increase visibility on the website of sort of the ability to ask questions. Like, I think people are kind of sometimes put off by emailing help, but you know, we're thinking sort of large buttons like, you know, have a question about whether ECSS is right for you, or want to talk to somebody before you put in the submission, and just kind of make it a little bit more obvious that we're open to questions about that. Because I think you're right. People are kind of put off, even though it's not a huge jump. And I think they also can think that it commits them to an awful lot. And if you request an ECSS and, oh, gee, the student leaves and suddenly it's not a good time for this kind of collaboration, it's okay. You know, it's sort of no skin off our back. We're happy to collaborate when it is a good time. But I think people feel like everything has to be set up to go perfectly before they put in a request, and that's maybe not necessarily the case. So thanks for making some good points there. And with 5 minutes to go, I wanted to give Sever a chance to answer the same question. And this is sort of about advising folks, especially from domain areas that maybe don't think about high performance computing an awful lot. Kind of what you would advise someone who's thinking about requesting support or using supercomputers really more generally.
Well, I would reinforce the idea that you have to be well prepared. Now, you know, any good programmer will, I'm sorry, it's my phone here. Any good programmer will figure out what your code does eventually, but it helps. It helps a lot if you have documentation and explain better what your code does. That will reduce greatly the time for everybody. The other thing is, I'm sorry, I was very lucky to have good collaborators in Paul and Bob, and we also talk regularly about this. We have conference calls with Craig, with Alan Craig, every other week, and we exchange idea, we consult, we share again experiments and idea, and that is very helpful and actually obvious, but you have to do it.
Great, thank you very much, Sever. We did have another question come in on chat regarding sustainability of science gateways and kind of plans that people had for continuing the operation of those things. I thought that was sort of a difficult question. I didn't necessarily want to put to my nice PIs here on the panel, but if anyone wants to jump in with thoughts on that in the remaining 3 minutes, certainly appreciate views on that. That's always a challenge for science gateways, even gateways that have been around for decades.
Yeah, I guess I could, oh, sorry.
Go ahead, I'm sorry. Go ahead.
I was going to chime in, just say that, yeah, I think that should be one of the first questions if someone ever comes to ECSS looking for science gateway support or building, would be from day one, starting to map out the strategies for this, because government funding is hard to get in long time scales. NSF, the fact that NSF only does one application a year is really, really too slow for my field. And so you just can't depend on it.
Yeah, good point. Jian?
So the model we are currently following is actually the NanoHub model. Basically, I'm not sure you other people here know that NanoHub, they start with the material science schedule, and then they have a Hub Zero portal spin out as a non-profit organization, probably a company. I didn't look into that, but that's the way how it goes. So for our development for simulation, we are trying to abstract out all the application-specific parts from the simulation framework itself. So we are trying to see if we can leverage the same computer science related components to other models like climate modeling that we are talking with people now, and some other modeling frameworks that we can integrate. And so by doing this, we can have some extra value added to their proposal and their writing, request for funding or other stuff. Particularly if it's a computer, if a coastal modeling related project, this might be working, but your value you added to the existing community might be not much. So it might not be helpful for just staying in the same community for a long period of time to get money every year to support yourself or other developers. I'm just saying, find a way to alternative to leverage your expertise. Of course, if you are a domain scientist, it's a different issue. Then probably focusing more on the domain science part and use a model or use your science schedule every time as some extra components in your proposal. That will definitely be helpful. So that's basically what currently we are doing here.
Great, thanks, Jian. Cameron, I wonder if you had any thoughts. Is your gateway in the early stages at RPI, or is it?
Yeah, I'd say early, certainly in terms of user base. We've been pushing functionality, but onboarding users is a somewhat of a slow process for us, and attracting the right kinds of users and such. But to echo the last comment, we included in proposals as far as outreach to add it as a value add to the overall proposal, and the lead developer on the application that the gateway wraps has a conceptualization NSF project through that I believe will partially fund the gateway.
Yeah, that's a nice strategy as the broader impacts portion of science work. Yep. Well, that brings us to the top of the hour. Want to thank our PIs once again. This has been really interesting for me, hopefully for other people on the call as well. Really appreciate your time having this conversation. And I will take plenty of notes so that we can improve the program with your terrific suggestions too. This will also be recorded, so if there are folks who are thinking about ECSS, they'll be able to listen to this and hear about the perspectives from your point of view. So thank you very much, and thanks to everyone on the call. And we hope that you'll join us next month for the next ECSS Symposium.
Thank you.
Thanks, everyone.
Bye-bye.
All right.
Thanks, Nancy.